In this video, we're going to implement Banker's algorithm. So, the C++ program here. We'll start from the main function here. So, first we are taking the inputs for number of processes and resources. So, and here are some initializations: allocation array, maximum array, and these two arrays we need to take the input from the user, and this two-dimensional array has to be calculated manually. And this is the allocation array. That means the number of resources allocated for each process at time t, for example. And it's a two-dimensional array. The first here you can see P and R. P denotes the rows and R denotes the columns, right? It actually represents the number of resources allocated for a process, allocated for each process. And after that we have another two-dimensional array, that is max. That actually represents the maximum number of resources that can be allocated for process P. So that is again a two-dimensional array. And after that we have two-dimensional array need, which has to be calculated manually, making use of these two 2D arrays. And after that we have 1D arrays, two 1D arrays, and this is available array, which defines the number of resources currently available, such that the process, any random process, can complete it to its execution. And after that we have Boolean array, that which is just to check the whether all the processes have been executed or not. This is a Boolean array. It contains either true or false, right? So if a process has been allocated, that means finished, then we'll change the status here in this array. And after that we have a save sequence string here, just to maintain the order of the sequence, that is a save sequence. And after that I'm taking the input for the two-dimensional arrays here, using the nested loops here. The first one happens to be for the allocation array, and second one I'm taking the input for the max array. After that I'm taking the input for the availability list, that means the maximum number of resources available initially. Fine, that is a one-dimensional array. And after that I'm calculating the value for the need matrix, which happens to be need matrix actually denotes the number of extra resources that are needed for the process to complete to its execution. That means that maximum resources minus the number of resources that have been already allocated, that gives us the extra need, right? So that one is actually this matrix. After that I'm considering a new request, and I'm taking a process number. For example, the process number is 1. Then it checks if the process can be allocated immediately, then or else if not, then the process has to be wait, right? So I'm getting the process number, and after that I'm taking the enter request for resources, and I have initialized another array here. Fine, and I'm using two check variables, and here I'm checking if a requirement is greater than need, right? If requirement is greater than need, then I'm giving 1, I'm updating check 1 is equals to 1, and I'm setting 1 here. And or if request 1 is greater than availability, then I'm giving check 2 is equals to 1. And if both are 0, then the request can be allocated, right? So if the request is less than need and less than availability, then that process can be allocated. Or else if check 1 is equals to 1, then process has exceeded its maximum claim. That means if request that resources are greater than the need, then we'll print this message. Fine. After that I'm having a while loop. This is for all, this is for the new request. From here to here, this is for the new request. And after that I'm using a while loop, infinite while loop. And we can see here inside the for loop we have a condition: if finish of I is not equals to true. So for example, if initially this array contains all zeros, that means all false, and if then if any entry in this array is not equals to true, that means only if this finish of I is not equals to true, then this if body will be executed. That means that once we set an item in this array is equals to true, that means that the process has been allocated or it has been finished. Now I'm using a flag variable. We can see here if need greater than availability for that particular process. Here J represents the process number, and we are setting a variable flag is equals to 1. Fine. then we can say we can assume like the process cannot be completed as of now with the available resources. So uh, uh, I'm checking a condition here. If flag is equals to 0, if flag still equals to 0, then we can allocate the processor for that. We can allocate the CPU for that process, or else we can proceed to the next step. If flag is equals to 0, then we can see can finish if y is equals to true. I've set true in this array. That means the corresponding process has been finished. It states that, and I'm adding this corresponding index to the save sequence as well, and I'm giving this print statement. And after that, the step is I'm using a for loop to update the availability list. So once the process has been finished, so the resources that are allocated for that process will be released, and those will be added with the entries in the availability list. That's what I'm doing here. After that, I'm just printing the uh, resources that are currently available. After that, I'm printing the closing parenthesis. That's it. And after that, this here ends the first for loop. And after that, we can see here I'm checking for the breaking condition to break the while loop. So break the infinite value, and I'm declaring a variable in temp is equals to 0. And you can see if finish of I is not equals to true. That means that if any of the entries finish of I is not equals to true, that means if any entry in the finish is false, then we are setting temp to 1. So that means that some process still has to be executed. So if temp is equals to 0, if it is still 0, then we'll break the infinite loop. So after that, I'm just removing the last character from the save sequence. Right, we have some symbols in between the processes, right? So that will be removed. And after that, I'm adding this closing parenthesis, and I'm just printing the results here, system in save state, and the save sequences I'm printing the string save sequence. Fine. And after that, I'm just printing the matrices here. That is, the first one is the allocation matrix, and the second one is the max matrix, and the third one is the need matrix. Now we're going to check with some random test case. So I have a sample input over here. We'll test this code with this input. This is the input here. Let's now enter the number of processes. That is 5. Number of resources is 3 for each process. Details for process 0. It is 0, 1, and 0. Those are the resources allocated for the process 0. After that, max. That means these many resources, that is 3, 2, 2, can be given to the process 0. After that, details of process. Sorry, I have given the wrong input, right? Now enter the number of processes 5. Number of resources is 3. Allocation is 0, 1, 0. Resources have been allocated for the process 0, and maximum resources are 7, 5, and 3 are the resources that can be allocated for P0 at high cost. And for P1 it is 2, 0, 0, and 3, 2, 2, and 3, 0, 2, and max for P2 is 3, 9, 0, 2. And after that, for P3 it is 2, 1, 1, and max is 2, 2, 2. Details for P4 is 0, 0, 2. Max is 4, 3, 3. Available resources, let me give it as 332, and process ID, process number, let me give it as 1 and 102. This is the request for resources, and we can see output is the same as given in the document. That is, P1 is listed for. This is a safe sequence: P1, P3, P4, P0, P2. So if the system executes in this order, then we can avoid the deadlock. That is the main concept behind the Banker's algorithm. So at each process we can see the maximum resources and the need, and here we can see if when P1 is visited, the available resources. I hope the output is correct, and thanks for watching.